Thank you for your interest in Bharat AI SOC Student Challenge. This initiative, driven by ARM and ARM Education, aims to support skill development in India by encouraging students to tackle industry relevant problems and devise innovative and impactful solutions. We are proud to partner with Mighty C2S program as well as collaborate closely with IIT Delhi, our lead academic institution in this endeavor. I extend my gratitude to Ministry of Electronics and IT as well as IIT Delhi for their support in this exciting initiative. Good luck to all the participating teams.
Hello everyone, I am Kulsum Ilyas. I am currently a Master of Science by Research student at IIT Delhi, where my research focuses on PCB development and design. I am also the program assistant for the Bharat AI SOC Student Challenge. Today, I will be guiding you through problem statement 3, real-time road anomaly detection. In the world of AI, we often focus on huge models running on supercomputers. But in the Bharat AI SOC Challenge, we are bringing that intelligence to the edge. My background in the hardware design has shown me that the bridge between software algorithms and physical hardware is where the real engineering happens. Today, we will discuss how to build a system that does not just work in a lab but works on the dashboard of a moving vehicle. The technical core of this challenge is to build a production ready application on the Raspberry Pi 4. We want you to process live dashcam footage to identify anomalies like potholes, surface cracks, and unexpected obstacles. While this sounds straightforward, the true engineering challenge lies in edge constraints. Unlike a cloud based system, your application must autonomously process every frame locally with minimal latency. This means you need to manage resource constrained hardware while maintaining a high level of accuracy, a classic trade off in embedded systems. The real world impact here is truly significant. By detecting these issues early, we can reduce vehicle maintenance costs and significantly improve driver safety by identifying dangerous road conditions before they lead to accidents. From a governance perspective, these tools help municipalities move away from slow, manual reporting towards a rapid, data driven response to infrastructure damage. Your work will generate the kind of insights needed for long term, intelligent infrastructure planning, ultimately creating smarter and safer cities. To succeed in this project, you must hit several key benchmarks that bridge the gap between a lab based experiment and a production ready solution. First, your model must be optimized specifically for the Raspberry Pi's ARM architecture. We aren't just looking for code that runs, we are looking for code that excels. This means moving beyond standard Python implementations and leveraging tools like TensorFlow Lite, ONNX Runtime, or the OpenCV module, which are designed to utilize the Pi's Neon SIMD infrastructures. By applying techniques such as int8 quantization, you can reduce the computational overhead, allowing the ARM Cortex A72 processor to handle complex math much more efficiently. Second, our speed target of at least 5 frames per second is a critical functional requirement. In a real world scenario, a car traveling at 40 km per hour covers about 11 meters every second. If your system only processes 1 frame per second, it could miss a pothole or a hazard entirely before the AI even has a chance to see it. Hitting the 5 frames per second ensures that your detection is near real time, providing enough lead time for the system to log the data and for the driver to be alerted. Finally, your system must be environmentally robust. A model that works perfectly under soft office lighting may fail completely when faced with the harsh glare of a midday sun, the long, deceptive shadows of late afternoon, or the low contrast conditions of dusk. We want to see how you handle these variables. This robustness is directly tied to your precision focus. A successful project must minimize false positives. If the system logs a tree shadow as a pothole, the data becomes noisy and loses its value for city planners. By ensuring high precision and robust performance, you make your logs truly actionable and useful for stakeholders who rely on this data for infrastructure maintenance. Let's look at the pipeline you will be building. It consists of four distinct stages designed for low latency anomaly detection on resource constrained hardware. Stage 1, Video Input. This begins with capturing a live stream via the Raspberry Pi camera module V2 or a 1080p capable USB webcam at an optimal resolution. You must balance resolution with processing speed. Too high a resolution will overwhelm the CPU, while too low will miss small cracks. Stage 2, Pre-processing. Here we use optimized OpenCV operations for frame resizing, normalization and color space conversion. This step is vital to ensure the input data perfectly matches the dimensions and format expected by your neural network. Stage 3, AI Inference. This is the most critical stage. You will deploy quantized TF-Lite or ONNX models specifically tuned for the ARM Cortex A72 processors found in the Pi 4. This is where the heavy mathematical lifting happens, and efficiency here determines your final frames per second. Stage 4, Action and Logging. Finally, the system must take action, drawing bounding boxes around detected anomalies, generating precise timestamps, and saving these annotated clips to high-speed storage for later review. This creates an automated record of road health without any manual intervention. For your hardware, we recommend Raspberry Pi 4 with 4 GB or 8 GB of RAM. This extra memory is crucial not just for the model itself but for managing large video buffers and ensuring the OS has enough overhead to remain stable during peak loads. Critical storage trip. A component often overlooked is the storage medium. You must use a high write speed micro SD card, specifically a class minimum. Standard cards cannot handle the constant, high bitrate data stream required for continuous video logging, which will create massive system bottlenecks and potentially lead to data corruption. Software stack. On the software side, we strongly advise using the 64-bit Raspberry Pi OS. This version provides enhanced performance and better memory access patterns for ARM-based AI workloads. You will also need standard libraries like Python 3.8 Plus, OpenCV 4.x for processing, and inference engines like TensorFlow Lite Runtime or ONNX Runtime that are specifically optimized for ARM hardware. You don't need to collect your own data from scratch. In fact, we recommend against it to save time. Instead, use established datasets like the Global Road Damage Detection Challenge, which offers diverse international road conditions, or the India driving datasets, which is excellent for challenging local infrastructure scenarios. Technical optimization. For maximum efficiency, I highly recommend exploring the OpenCV DNN module. It is specifically engineered for ARM processors and supports hardware acceleration, which can significantly reduce CPU load. Quantization. Most importantly, remember to apply int8 or FP16 quantization to your models. This process reduces the precision of the model's weights but vastly increases speed. It is the absolute key to achieving your 5 iframes per second target while maintaining the accuracy needed for reliable detection. Always benchmark your inference time separately from input-output operations to find exactly where your bottlenecks are. I want to highlight a very important technical warning. Cooling is not optional, it is essential. Continuous AI inference on the Pi 4 generates an immense amount of heat on the ARM Cortex A72 processor. If your processor temperature exceeds 80 degrees Celsius, the system will trigger thermal throttling to protect itself. Performance impact: this will automatically drop your CPU clock speed, causing your performance to plummet from a smooth 5 frames per second down to a crawling 1 or 2 frames per second. At that speed, real time detection becomes impossible and your system will fail to capture anomalies accurately. The solution: you must implement a robust cooling solution. Use active cooling fans or install high quality heat sinks with thermal paste to ensure your system can maintain sustained performance throughout your entire demo. Finally, your submission. We want to see your clean code on GitHub, your optimized model, and most importantly, a demo video. Show us that your AI can see the road. If you get stuck, remember we are here to help. Reach out to tech queries at armbharatchallenge.com. We are not just looking for code, we are looking for the next generation of SOC engineers. Good luck.